Okay, cool.
I used to be so bored. Wait, are you
Yes,
I saw your emails and I realized, oh, this is what we talked about. So you're okay? Okay.
He's extremely increasing, but I think it's
Let's test it out.
Okay.
I'm really thinking on this critical point today, you guys.
The what?
What?
Critical point?
Yeah, it's very critical.
We have to talk critical
That's a
point.
very critical point that we care about.
No, you guys are cooked. It's not cooked, I'm saying. You guys are fried, right? Because you have a you're tired. You're,
Oh, we're tired.
yeah.
Oh, where is that? Actually, there was
Okay. So, I have 2 goals for today. One of them, maybe you'll like more than the other. The first one is going to be that we are going to, we're going to teach a new topic. And number 2, we're going to review the test. Which one will you like more? I don't know. So exam, I just ordered it to get printed, so we have all set. I'll have 36 copies. You can take one home with you once it's done. There's fewer than 36 of you. Should be fine. There'll be 4 questions. Yes, no.
4 questions.
5 questions.
5 questions. I wonder what those 5
4 or 5 questions. You get an hour 15. It's not going to kill you. It wasn't made to kill you, but maybe I'm out of touch. The only way we find out how you guys are doing versus how you're fronting is how it goes on this exam. But I can promise you one thing, it will be entertaining. Okay. And it will cover everything up until Wednesday's lecture. Are there any questions? You're asking questions that are going to make it really hard for me to not tell you information. You shouldn't do that.
I was just wondering, there's a computer.
There is now, because I was going to go to bed at 11. And then the redhead and I were watching this movie called House of Dynamite, which is the one where there's almost a nuclear war. It's got Idris Elba in it, that's on Netflix. Anyhow, but then she said, no, let's watch Finding Nemo. And usually when a movie is proposed after 11 p.m., one of us falls asleep within 10 minutes, but this time it was her. And I watched Finding Nemo through to the end, and I finished it at 2 in the morning with a tear in my eye and an itch to do more. So then I wrote a practice test. And it's on Canvas.
Is it on the same general topic?
It is on the same, yeah, it's not going to have, it might have a little bit on what we do today, but that's good practice anyway.
Okay.
But for the most part, no, it'll be useful. I made it useful.
Hooray.
I ran it through chat.
Oh, not
chat.
Claude?
Not,
Wow, we're not good enough for that.
No. So I give Claude my journals. I go through my innermost thoughts with Claude. And I don't want it to leak, to bleed that into the exams accidentally, so. Christian childhood trauma winding up in your text.
We're not good enough for our prompt, guys.
But you know my parents are divorced, and that's how you know chain rule, right?
That's true.
All right, so 2 things. Number 1, no. We're going to keep to the mission, and then we're going to review. Sadie, do you have another question? What was your question just now?
I was just where.
Oh, about the practice test? Yeah, it's on the canvas. Check, please, but it should be on the canvas. Okay, so review of chain rule. Are we all good on chain rule? So if we have, let's say Jacobian from UV to TS, what's the same thing as, what is another way to write this with the same meaning but different notation? D what?
UV over US.
Over DTS. Beautiful. What if the top thing wasn't just one function of T and S? Then what would this just look like? Let's say it was U as a function of T and S.
DU.
DU DTS. And this, if we go through the matrix multiplication, what Jacobians is this a product of? DUV, D. Oh, yeah, sorry, so I should say UV, XY, TS is the progression.
DU, XY.
Yeah.
XY, TS.
Yeah, you got it now. Cool. And as a product of Jacobians, what does that look like? What's the first Jacobian? So this is Jacobian UV to XY. Someone give me some terms of what goes in this. First off, how many variables are UV? 2 of them. How many variables is XY? 2. So how many elements are in this matrix? 4. It is a 2 by 2 matrix. What is the first row? Yeah, du dx du dy, and then dv dx, dv dy. Okay, and someone new give me the other matrix. Okay, on someone. I locked eyes with Diego. How do you say your last name? Abadi. Where is that?
It's Basque.
Oh my, do you speak it?
How much?
No, because it's a unique and complicated language. Wow. You speak like Catalan or something?
No, just Spanish.
Spanish. Okay. All right. So this is Jacob. Okay. So Diego, what do you got?
Dx dt. Dy.
Oh.
Ex d.
Dx. Yeah, I always screw up as well. And then here we have dy dt.
dy.
Yes. Okay. Awesome. And then if you do the matrix multiplication now, you're going to end up with a whole bunch of. You're going to end up with 4 things. Right? And what are they? You can either multiply this in your head, that'd be fun, or you remember what we're looking for, uv to ts, and you know how this works out in the end. So if it's a Jacobian from uv to ts, and these products give you that, what should come out of this end? du dt, brilliant, and then dv dt, dv ds. So there's a little bit of exam review stuff in here, yeah. And if you multiply these out, you will see this, because you are going to have something akin to, for example, let's say this element, du dt. You can find that by multiplying matrices. What's another way you can find this? If you know that u and v are functions of x and y, which are functions of t and s. What is the really reliable way to draw this to bypass some of this, or to just sanity check? We have at the top, we have u and v. What do they depend on? X and y. Both of them depend on x and y, right? So u depends on x, y, v depends on x, y. And lastly, they both depend on t and s. This is one way you can write it. You can also write it this way. U depends on x, y, which depend on t and s. Y depends on t and s. So, but I have to do the same thing for v. So it starts to get messy, right? But there's no reason you can't do this. Oh my God. I say as I behold the awesome extent of this. These mean the same thing. What are we seeking in the end? What are we seeking when we're trying to find, for example, du dt? Tell me things. What do we do at the very beginning? What's that first step? You want to try one?
dx dy, or sorry, du dx times dx dt.
Times dx dt, right? Or, yeah, so through u, x t. So, du dx, dx dt. Are there other ways we can get to t through from u?
Yeah.
You've got it. We can go through y and t, or again we can go through y and t. So that's the product of those partials plus du dy, dy dt. And the thing I want to drive home here that never hurts to drive home more is that this, right, this alone is not du by dt. Right? This is the whole step-parent situation. Or there were no step-parents in Soga. The divorced parents, yeah. Help me out here before I go into a long-winded story. Du dx dx dt, what does that represent? In English, it's fine. Yeah, or basically where I'm driving at is, why don't these cancel out? Why is this not just du by dt? Right, it's the contribution through x, but it's not the only piece, it's the partial piece. So absolutely. Okay, cool. All right, so now we get to move on. Lingering questions about chain rule? Okay, we will now enter the wonderful world of finding extrema of multivariable functions. I am going to keep this here and then just switch the order of the boards later on. Okay, so in single variable calc land, you have the following. You had a function, and it looked like this, and maybe sometimes it looked like this, and maybe sometimes it looked like this. This is a wonderful way to see all of the pieces. This point is called A, this point is called B, and this point is called C, and you all are getting your AP scores soon, right?
Yeah, that's right.
Oh, why didn't I hear people get into tomorrow? No? You, all of your AP scores are just Calc? Oh.
We're old news, it's old news.
Because I remember you talked about it last week. Okay, anyhow. So you know how you did an AP Calc, and you remember AP Calc, so what am I trying to say here?
When the slope is 0.
When the slope is 0, we have an extrema. This is called a max, which is the 6th most common dog name. What is this one? I mean, I think it's just the 4th most common dog name, but you wouldn't have looked it up. It's like John Oliver when he said, a country you think so little about. You didn't even realize that that wasn't, that country. Except one of them was Venezuela, and being part of Venezuela, I do know where it is. What is C? Also 0 slope. But what's magical about C? What did you call that back in single variable calc?
Inflection.
Inflection, right? Max, min, and inflection. Not to be confused with infection, which is happening too, because it's the freshman plague over the summer, the pre-freshman plague over the summer. All right, so this is single variable calc, and now we're going to enter the wonderful world of multivariable calc, where Christian tries to draw three-dimensional things and two-dimensional boards, but come up to office hours and I'll slap a VR headset on your head, and you can view it the way that it was meant to be seen. And so here we go. We have something like this. We have something like this. Exactly. Something like this. Okay. So maybe you catch my drift, but here we are. And then here we are. And then somehow, somewhere here, we are some other place. And what I'm saying is that this is a max. This is a, ooh, I'm using a tangent line. Yeah, tangent plane. That's in tangent plane is here, tangent plane is here, and tangent plane here somehow is also flat, but we'll talk about that in a second. This is called the min, this is called the max, and in three-dimensional space we have the best name for an inflection point. If you don't already know the term because you learned it, I prefer to hear from you. Maybe we could derive the name together. Anyone know? Anyone into horseback riding? Yeah, saddle point, yeah. It's a saddle. A saddle point, they're going to come up with so many ways to teach it to you. I have one that is, some have said inappropriate, but I disagree. Everyone please stand up. Okay. Your head is a max. Your chin is a min. Chin, min. I literally just pulled that out. But the one I'm really here for is your saddle. We all walk around with saddle points, I hope, are pants. Along this direction, you've got a max, yes? Along this axis, you have a max. But along this axis, imagine you have this big rope and what do you have? A min. That's a saddle point. It's a max in one direction, a min in the other direction. And now you won't forget that while you're taking your chemistry test. We're not taking off our pants. Okay. What's the max?
Yeah, what's the max?
Oh, so the max. Okay, so go from your right leg to your left leg and arc that way. You gotta do it yourself. Let's. Bridgerton, let's. What do you think?
I don't know.
Oh yeah, absolutely, absolutely. Okay, so if you put this on your head here,
I'm so silly.
it's flat. Put this on your thing, and if you manage to fit this, you don't want to bow-legged, but you fit something, it will be flat. That's as far as I'm going to take it. But you remember, you got it? Okay, cool. Okay, and I don't know you remember, but you won't forget that something was about pants. It'll look really weird. I'm going to teach you about ATP when we do line integral. It's going to screw with you from biology. But let's just recap what we called these things in single variable calc in terms of tangent lines. So yes, you told me here that f prime was 0. What does that mean? That means that dy by dx is 0, dy by dx is 0, and at the inflection point 2, dy by dx equals 0. So how can you tell them apart? Second derivative test, right? Here, the tangent line is big slope. Right, positive slope, and then it's doing negative slope. So what is the second derivative at a max? Negative, which is weird because you want max, it feels like big and positive, but it's the other way around. Min, what is the second derivative for a min? Slope is negative, and then rising, positive, so what do we have? And what about at an inflection point?
It's just a 0.
I believe it's 0. My single variable calc knowledge disappears right around the time that yours is now. But that is a thing. Okay. And then you can also write that as, d squared f, dx squared. We remember second derivatives. Oh, sorry, now that we're turning your head to look at this. Oh, I saw you tilting like you couldn't see it. You good? That's fine. Cool. Bet. All right. So we got to figure out what the heck's going on here. And I bet you can tell me. Well, we have a critical point, an extremum. What do you think the name of the situation that has to happen has to be? If the slope of the tangent plane is 0, the tangent plane is flat.
Did you say that it's flat?
That's flat.
Oh.
Well, I guess it depends on how you define flat. This is flat, but it's on another axis.
Yeah.
But if the tangent plane is flat, what is the slope of the tangent plane? 0. So tell me more.
Df,
dx is 0. What else is 0? More generally speaking, what has to be 0? The gradient of f is the 0 vector. At all of these 3 points. So if we give you a multivariable function and we say, hey, find this extrema, that really boils down to you figuring out the point where the gradient is 0. Which ends up becoming what from a math perspective? I forgot the whiteboards, oh my god. Yeah. What does it become? You have to set the x derivative equal to 0, the y derivative equal to 0, so that just becomes a big algebra problem, right? 2 equations that equal 0, 2 variables. How about it?
2 variables, 2 unknowns.
We can do this if we got 2 variables, 2 unknowns, provided we lock in and have enough caffeine. Okay. The real core of what I want to talk about today has got more to do. Has got more to do with the second derivative test. And there is a way that the second derivative test is normally taught that just kind of gives you numbers or like rules to memorize. I think we have it in us. It runs through our bones. What's the song in Love Actually? I feel it in my bones. Yeah. That was gonna make this resonate for us. The resonance structure. You guys, no chemistry. Wait, there's a really cool dot product problem to derive that angle between the bonds.
No.
Yes.
Yeah, it's fun stuff. And it's a good Calc practice problem. I almost put it on the test. Almost. No, but it would have been like, oh, my classes, they're connected. Like, for what it's worth, when I took interface chemistry, I loathed it. Patty Christie wasn't teaching it either, but there was a mess of people teaching it. And I just memorized all of the Vesper stuff by writing it on my mirror in my dorm in Massey, which is where we lived during interface. It didn't have air conditioning, so it wasn't that much better. And I just memorized it all. But then I'm finding out that there are these beautiful, like, physical ways you can derive it. But you guys have it good, is all I'm saying. Okay. Back to math. Yeah, back in my day. I think it was even in this very classroom where we had the final for Calc. And I copied all the best. Every board I could find at MIT, I walked into the room and I copied the Vesper stuff, so I had it memorized. But it was soulless. And now maybe it's not. Okay. What the hell am I talking? What was it?
Second derivative test.
Oh my god, thank you. Okay.
Wait, a second derivative.
Yeah, okay, so now I'm going to ask you a question, which is a function at an extremum, or a function at any point in single variable land. We had a nice little thing we could do, which was to approximate the function with a line. Yeah? Okay. Now, that is cool, but it's not the end of it. What was the other level of approximation? Everyone's favorite. Chalk keeps getting my eye when I talk about quadratic approximation. I wonder why. It's called quadratic approximation. So here's your linear approximation, and quadratic approximation, which is going to be some other color. Let's call it red, because of how important it might be. It would look like this. Okay, and this is another conversation. If the function has a max, what else has a max at that critical point? the approximation does. Now, we don't talk about maxes and mins for linear approximation because it's a line. We don't really do that. But do you agree with me that if I approximate my function around this point, my orange function around this point, with a parabola, that they will have the same max or min?
Yes.
Okay, so will it surprise you that my next thing will be to ask you what the equation of the quadratic approximation of a function is? Delta f is approximately, ooh, I think Loyan wants to answer this. Ooh, yeah, you asked really cool questions yesterday. What do you think? Oh, yeah. So I guess I had delta f written here, but there's no reason we can't do it this way. So f at x is approximately f at, go ahead, x naught. Okay, what does this mean in English? Yeah, well, not the origin. Well, what do you mean by origin? Yeah, at the point where you're doing the approximation. Yeah, when you say origin, I was thinking 0, 0. But that would be a convenient one here because then the numbers get prettier. Okay.
Plus f prime.
Yes, but go multivariable calc on me because this is a vector. Yeah. Yes, gradients of f evaluated at x naught dotted with. Yep, delta x vector. Right. Okay. And let's remember what this means in single variable land. This is called f of x naught plus, what is this in single variable land? The gradient of f is just called, or yeah, you'll do f prime, sure. Right, f prime evaluated at x naught times delta x. By the way, what's delta x in both of these cases? Change in x, but like if you wanted to expand that, what would it be?
X minus x naught.
X minus x naught, and in vector form? Yes, with right. Or x vector minus x naught vector. When I write x vector, what am I referring to? X and y, or if I'm in a higher dimensional space, every dimension, x, y, z. So x minus x naught, y minus y naught, z minus z naught, where your starting point is x naught, y naught, z naught. All right, but now this is where things get exciting, because we do need to bring on our quadratic part. You're going to do the single variable version and the multivariable version. Okay, you guys are hardcore. Okay, we're not even going to go with the babying into things. Okay, what do we put here? 1/2, and then,
Transpose?
Oh yeah, is it x or is it?
Delta.
Delta x transpose times the Hessian evaluated at x naught. Hessian. Oh, what did you call the Hessian? Hessian. Una serpiente. Delta x vector. Serpiente.
And this is supposed to be easier?
This is
Go back
supposed
to
to.
maximum?
Oh no, it isn't. Because we're not using this to find it anymore. You're good at finding gradients. What did we say here? We said that. Oh, sorry, I never really gone into it.
The max over there is the same as the max over there.
The max over here is the max over here. I agree. And what are you really good at figuring out if it's sloped like this or like this in single variable calc land is a parabola. It's really easy to look at a parabola and say, ooh, that has a max, or ooh, that has a min, right? Because of stuff you memorized at some point in your life. Oh, or actually, there's an even easier reason why it's easier. What's the second derivative of a quadratic function? If it has an x squared in it, and you go 2 doors down, 2x and then 2, right? And whatever the coefficients are, they just add magically. The point is that you're able to see right away if the second derivative is positive or negative. More specifically, guys, the second derivative of a quadratic function in single variable land is a number, right? This might be some crazy x to the 5th plus, some crazy polynomial fit about your hours of sleep that's like 7th order. But if you approximate it around this point and it's a second order, that baby parabola that you're using, you can find the second derivative really quickly, right? So you can already tell something about that approximation parabola, whether it's a max or a min, right? And that actually tells you something about the behavior of this function near this area without you needing to take some weird way of finding whether a point in the x to the 7th is a max or a min or something. All right, does that make sense? Danny, you have a question? Oh, Andy, why did I call you Danny? Because Edmund Trejo Valdes' brother is named Danny. That's what we do all that. Okay. Okay. Oh, and Andy's in Mike's. No, Danny's in Mike's. Andy's in it. Okay. Yeah, but I know you. You're not Edmund's brother. All right, any questions on the motivation for me doing this? Good?
But how do you?
But how do we do it? Aha, well, this is our second derivative, okay, this is our quadratic approximation. So we agree that the parabola, the paraboloid, the quadratic approximation tells us about the behavior of the function locally, which will mean it will tell us if it's a local max or a min or something else, right? Okay, to go into further detail about it, we know it's the second derivative piece that gives us the information. This term contains everything we need to know about classifying the critical point as max, min, or sal. Okay. I can do math on the board, but I want to make sure, we need to ask a question here. There's this thing, it's a stupid question, this is supposed to be obvious, and there's no reason this has to be interesting, especially when we have an exam next period, so why should you care? So please ask away. Yeah, I heard a groan, I heard a moan, I heard it all. It hurts. Here's a thought. Look at the person next to you and explain to each other this. And if there's a breakdown, and then you'll tell me.
Yeah, you got that.
Or take turns explaining it to each other. Yeah, that makes sense.
And the quote, and this
oh yeah, that's true.
So I mean, all that really matters when we do this, because I was actually not, plus that part, with that part, plus or minus should tell us everything.
Yeah, the behavior of this context is good. Yeah, that's especially why we care. It is the equation of the parabola at the critical point of gradient is I know it's just minus. It's like, oh. Gives you positive numbers, then for all coordinates, then you know that this is always so that's plus and then something always you know the 5 is if you have 5 plus, you know it's always decreasing. Oh, getting rid of 5 stays value.
We are seeing 801 to go to 802, guys.
Yeah, we have the max.
Oh, yeah. 70%.
By x I mean 4, it's not
But,
all right. Okay. So from this conversation, this bunch of a theory of the universe might have emerged. I already know that Vaughn is the one who asked me about this. No, what was against say?
The graph?
No. But who? Oh yeah. All right. So at the critical point, guys, what's the gradient? 0, right? So actually, the quadratic approximation at the critical point. I know I said this is the only point that you care about, and you can take my word for it. But another way you can see it, other than Christian and lecture theory, is the gradient is 0. So the quadratic approximation of the critical point doesn't have any linear terms anyway. It is purely where you start plus this term. Does that make sense? Okay, but now someone explain to me what came of your conversations just now. Yeah.
It determines curving up or down in the z direction.
Yeah, if it curves up or down in the z direction, but keep going. But like a slightly bigger picture. Why do we use the quadratic approximation at a critical point to classify it?
Because the tangent plane can't tell us the direction.
Correct. So what does the quadratic tell us? Or what's the benefit of the quadratic then, other than that it's not 0?
It can tell us the direction in which the function is curving.
Exactly. The curvature, so to speak, at the critical point of the quadratic approximation is the first clue that we have about the behavior. Right? There's no curviness to a linear approximation. The very first hint of curviness we get is when we go 1 degree further, which is quadratic. And when we go quadratic, it's impossible. Is it just? Yeah. No, it feels weirdly hot. Then the very first time you get curvature is from the next degree up, which is quadratic approximation. And quadratic approximation, quadratic functions, they have maxes and minis and otherwise. So, are we good? All right. So, are you convinced? Have to be, but are you convinced then that this term is what tells us about how this function behaves at the critical point? This is the key to classifying the curvature. Yeah? I don't hear any objections. So now I need to talk about a property of a matrix that is actually really cool. But before that, let's just write in a super from now on, this is the Comic Sans chalk, which means you get to you don't take it seriously, right? Because it's much more loosey-goosey. So let's do Comic Sans in green actually, and we're going to say that f of x is the starting point. So this is moving very loose, plus something. Something that relates to x, right? The approximation of our function is wherever we began. So let's write that as like a green dot. And then something in terms of x. Let's say that the extremum, the critical point, is here. If it's a minimum, what does that look like? What does the rest of this curve look like? That means that something term that you're adding to this, start, is it always positive or always negative? Right? If I start at 5, let's say this starting point is 5. If this is a minimum, then everything else in the function has to add to 5. Does that make sense? So we're good. It's okay. Yeah.
What do you mean by add to 5?
The something term is always positive, right? Because then 5 plus 0.1, 5 plus 3, 5 plus 29. If this something is guaranteed to always be positive, then 5 is as small as things get, because it's always 5 plus something. Does that make sense? Yes? No? Doesn't? Okay. Now, what if the something were negative all the time? Then what would this look like? 5, and then what am I always doing to it?
Going down.
Going down, right? In that case, if this something is always negative, what is my critical point? A max. So this is a max in the case where the something is always negative, and a min in the case where something is always positive. Okay, please take 1 minute and explain that to each other as well. I think this is good. This is the beginning of the pyramid scheme. There's more like dipole scheme.
You're doing like a theoretical. You're adding a theoretical.
Wow, no, it's not to go ahead. We can pull it up on the, we can pull it up on the back. Remind me in a second. That would be
Wait, no! We only give one signature. You go up and down.
There's something that is the quadratic.
Yeah, like, I couldn't have known that adding a lot of things basically like okay, wait, so like actually walking where it's supposed to be like I think it's wait, 0.1738 minus
There's a bunch of ways to interpret it as it's not the sign. But there's other ways, so there actually like 5 different criteria.
checking in on
Each of them makes the other to check information. It's positive.
it's closer.
All right, everyone. All right.
No, he's.
What? Oh, were you guys in the middle of it?
No.
All right, you sure? All right. How did the conversations go? Someone explain to me what we just said. Like what you got out of the conversation. Hi, Sadie. You gonna tell us stuff?
It's just because if it's open and upward, then it has to increase.
Yeah.
So just that something has to be positive.
That something has always to be positive, beautiful. Or if it's a max, then that something has to be negative, beautiful. And what is that? So how does this convert to this? What is the start? In the quadratic question, what is the start? Yeah, f of x naught. And what is the something of x? Yeah, the quadratic, the term with the hash. Okay, and now I would like to bring up Lily, who is going to explain the next piece. You ready? Yeah. All right. Woo! We believe in you. If you mess up, it's fun, right? But we're all learning together. This is wonderful. And you volunteered. This is awesome.
So, we kind of said that if the Hessian is always positive, it's a min. If it's always negative, it's a max. But if and you find out whether it's positive or negative using the eigenvalues of the matrix. So if the eigenvalue is always positive, you get the min. If the eigenvalue is always negative, you get the max. But if it's like a mix or something.
If it's positive and negative.
If it's positive and negative, then it's indefinite, so it's a saddle. And if the eigenvalue is 0, it's like inconclusive or like.
Yeah, inconclusive. Yeah. All right, cool. All right. I'm going to break that down because I also didn't explain to these guys the breakdown. So There is a property of a matrix. So actually, first off, is everyone clear on why we would care that that something would always be positive or negative? Because that dictates whether you're going up or you're going down, and therefore whether you're a min or a max. Now, matrices are not scalars, so like the second derivative is a number, and immediately you can tell if it's positive or negative. A matrix isn't. At the level of matrices, we don't have positive and negative matrices in that same sense. We have a property of a matrix that tells us whether or not it will always give us positive outputs. That property is called positive definite. A matrix is positive definite if, give me a vector, pick a vector of x, y.
Well,
I guess I meant more generally. If x transpose AX is greater than 0 for all x.
which is C1 squared, like the whole thing we did last piece on.
Oh, but that's only if you, that's if it has, or if it's a
Symmetric.
symmetric matrix, so yeah. This one, although, wait.
No, it is.
The Hessian is
C1
a
lambda.
symmetric matrix.
Oh, it is.
Yeah.
Because f of x, y, and f of y, x are equal.
So okay, wait, so that's a really good point. This is a property of symmetric matrices, which the Hessian is. So we're in business. If x transpose AX is greater than 0, then A is positive definite. X transpose AX is the quadratic form of this matrix, which we've seen, right? If we have vector transpose matrix vector, vector transpose matrix vector, if this is always positive, then what kind of critical point do we have? A minimum. Similarly, what's the opposite of, what color do we make negative? Yellow? Okay. Negative definite. Instead of positive, here it is.
Make it keep rolling.
Exactly. So if the matrix is positive definite, then this is always going to be increasing, so we are at a min. If the Hessian is negative definite, then this is always negative, so this is always decreasing, so this critical point is a max. Oh, and it even worked out with the coloring. The yellow gave us the max. Wow. Was that behind your suggestion? That's well done. Oh, yeah, I planned that.
So do we
I
have
planned for you to plan that.
to, so do we just have to solve for that function?
No, because this is the biggest pain in the butt that ever exists. So it turns out, take 1806 and you will learn 5 ways to classify a matrix as positive, definite, negative, definite, or otherwise. We're not going to learn those 5 ways. There's one really straightforward way to do it, and if you diagonalize, you can prove it. But what it means, what it says, is if all of the eigenvalues are greater than 0, we are positive definite. So what do you think the next step is? If all of the eigenvalues are less than 0, then we are negative definite. And there's one more case, right? Okay, so if all the eigenvalues of the Hessian are positive, we're positive definite, so what is our critical point? It is a min. If all of our eigenvalues are negative, then our matrix is negative definite, so we're always going down from f of x naught, which means we have a max, fourth most common dog. And last case, what's our missing critical point? A saddle. If all the eigenvalues, maybe we make this orange, if all eigenvalues are greater than 0 or less than, are a mix of greater than 0 and less than 0, then we're called indefinite. And we have a saddle. What's the missing case over here? Greater than 0, less than 0, or a combination of greater than 0 or negative, or greater than, or less than 0? What's missing? Equal to 0. Equal to 0? Test is inconclusive. And you got to plug in points or find some other clever way of classifying the critical point. we won't bother you with that case in this class, but it is a thing.
Great.
Wait,
Cool.
how do we know that the Hessian is a symmetric?
Ooh, this is fun. The Hessian is a symmetric matrix because, tell me, Invita, what are the components of the Hessian? If we have a function f of x, y, what is the Hessian matrix? What's the first one over here?
Oh.
You already,
You got it? Yeah, but you gotta say it now. You signed up for this.
X,
Yeah, second x partial. What's here?
F, X, Y.
Okay, here.
F, Y, X,
Okay, here.
F, Y, Y.
Okay, and what do we know about mixed partials?
They're
Yes, so if the off diagonals match, then this matrix is equal to its transpose, is another way to say it, in 2 by 2 land, and we've got ourselves a symmetric matrix.
I get it.
All right, so there's so much packed into this, and now you understand why. Yeah.
No.
Why is it medical symmetric? Because one of the properties for positive definite involves that you can express it as
N equals 3, this is no more
it's A is symmetric, and right is B transpose B, C is B,
We did it.
and that's yeah.
Okay, wait, it's just that. You got it a little too. There's nothing on my end.
Yeah, but for our case, it's always going to be so you.
You're it.
All right, guys, any questions on this? Yeah, Sydney. What's up?
How does eigenvalue related in this?
Excellent question. I didn't go through the derivation. So first off, you're asking this question not because of something that you missed or something that you don't understand. Is I actually never really said it, right? I told you that this is the case when we have positive or negative eigenvalues. So the derivation is missing. Would you like to try the derivation? Okay. Well, we could. Yeah, it wasn't a threat. If you ever want to, breathe again. But no, but it's not because you missed something. It's because you can show that this is proven by the eigenvalues.
Because X.
Is that all right? Because if you're not convinced, then I think you do want the derivation.
Yeah.
Okay, so I'm going to try the derivation briefly, and then we're going to review for the test. Is that okay with everybody? Yes? Okay. So let's try to derive the notion that if a matrix is positive definite, x transpose AX is greater than 0. And I think the best way to do this might be to start plugging something in, because this is going to be a pain otherwise. So X transpose, let's just work in 2D. What is X transpose? It has two components, it's X and Y, sure, why not? A is a symmetric matrix, so we're going to call it A, B, C, D, except that we're not, because if it's symmetric, B is equal to C, right? Is this fine?
Yeah.
Okay, this is almost Diego's last name. Abadi. Abdi. Where'd he go?
Oh, you missed it.
Why do I even try? Okay. And then we have x1. Okay, this is a good exercise in general. If you multiply, actually guys, work this out. I'm sorry, I'm thinking with markers. But multiply this out for a moment, and you're going to realize something. Oh, man. This is going to be fun stuff. Did I hit the button? I think I did. I think I did. Will you check out?
Yeah, it looks
It's
like
recording.
it's recording. Have the red
I have trust issues with the cameras. So what's the first thing we do? We're gonna what's the easiest order? Do you want to multiply this by this first, or this by this first? Probably these two, right? Okay. So what does this multiplication look like? A B B D times x y. What are the dimensions of it? A matrix times a vector gives us the column, the vector. Yeah. So we're gonna keep x y, and then this is gonna be what? Ax plus by. Ax plus by, okay, and what's the second row? Plus dy. Okay.
Can we add our x's?
Say again?
Can we add our x's?
But remember, these are different elements of that
Oh.
matrix. Yeah. This is a 1 by 2, this is a 2 by 1. Alright, oh, you missed it. We had a whole thing about a matrix with your last name. Oh.
It's still there.
Abadi. Oh.
Feel honored.
Okay. Unless you are a baddie, then we would. What is a baddie? What does that mean? It's an Instagram thing, right? I don't know. Is he a baddie by definition? Have you gotten this before? I don't know. It took me arriving in your life to troll you, know, someone else knows. Alright, so now if we multiply these out, what do we get now? So now it's a 1 by 2 by a 2 by 1. What is another term for, what is another word for what we're doing here? Dot product. Were you the one who said it that with that voice in the button back in the day? That was Vaughn. Alright, so what do we do? What are we gonna get here?
AX squared.
AX squared plus BXY, okay? Plus BXY plus DY squared, which becomes AX squared plus 2BXY plus DY squared. What's this? This is like a quadratic form. So this is the quadratic form of xy. The linear form of xy would just be something times x plus something times y. This is quadratic version. Anyway, what the heck does this have to do with eigenvalues? This is the thing, you did have a question about that after all, right? And I still need to save face, so I'm going to give it a shot. Okay, what are we trying to convince ourselves? We're trying to convince ourselves that this is always greater than 0 if we're positive definite, right? And I think this is where you crazy completing the square people starts to pop up. How can you prove that this is always greater than 0? I think what you would end up doing is you would group the terms in a certain way. Which, I don't know what you do. Oh no, maybe, yeah, you factor, oh, maybe you do this. Let's factor out an x. This is all supplementary. Alright, so if you factor out an x, you get ax plus 2b, right? And if you factor out a y, what do you get? dy plus, also, is this dy a derivative? We sure? Is this a derivative? No, it's just a number equal. Yeah, I want to make sure because there's so many letters here. Okay, dy plus, and then what else is there? Is it 2b as well? Is this a singular b?
Yeah.
Wait,
Well, no.
There's a term with y.
Oh, okay, so this is bx, and this one's by.
Wait.
No, it would just be singular by.
Yeah.
Ah, because then you add them, okay. Okay.
Wait, that means wait. Sorry.
No, it's fine,
That means each piece has to equal 0.
Each piece has to be. There's something here. Great exercise on the side. Yeah, we're going.
You could substitute x with an eigenvector of the matrix.
Oh, okay. But what would the eigenvalues show up?
And then replace a v with eigenvalue times v, and then you have eigenvalue v transpose v, which is eigenvalue times magnitude of c squared. It's greater than 0, so the eigenvalue.
That was it? You want to do it?
Yeah.
Like go to Alright. Do you all push big R, is that what you do? Oh yeah, for all X. Oh yeah, go. Alright. Oh, wherever you want to go, yeah. I'm gonna see. Very long story.
So something like you forgot to mention was that positive definite means that this relationship holds for all vectors x. So that's what positive definite means. So which means we could replace x with an eigenvector of this matrix. So let's see. So should let V be an eigenvector A, and then so we know that V transpose times A V is greater than 0. That's what it means when it's positive vector, right? So what do you know about A V? because it's an eigenvector, we know that AV is equal to lambda V, right? So now we have V transpose lambda V is greater than 0. And lambda is just a constant, so we just move stuff around. So this becomes lambda V transpose V is greater than 0. And if you remember from an exercise, I think it was P6, what is V transpose? What? So this is just V dot P. And what do you know about V dot P?
Magnitude.
Yeah. So V dot P is just the magnitude of V squared. It's just one of the P set questions. Does anyone remember that? Yes. Okay. So now we have that lambda times the magnitude of V squared is greater than 0. So what do you know about this square? What do you know about the square? So what does that mean? What does that mean? That means lambda also has to be positive. And now this works for any eigenvector of A, right? Because I didn't choose any eigenvector. That means all the eigenvalues of A also have to be positive.
So then, do you connect that with taking the determinant of the Hessian to see if it's full rank, and that says something about an eigenvalue?
This is just a Hessian. Like
Yeah, so instead of A, you
matrix
use H.
is full, it's positive definite. So replacing A with the Hessian, same with it. That tells you the eigenvalues of the Hessian. Does that make sense?
No, it does.
And if it's not full rank, what's an eigenvalue? Huh? Oh, it's 0. Yeah, if the Hessian isn't full rank, then eigenvalue is 0. Right. So then, yeah. So, but then this becomes not inconclusive anyway because we don't need the second derivative. Wow. I was feeling. Wow. All right.
So yes, the same argument works for negative definite as well. Because you get that this has to be less than 0, and since this is positive, so this has to be.
Very. Alright. Thanks.
Wait, we know the value of
That's so much cleaner.
Wow.
I was trying to make a mess of my quadratic stuff. Okay. So, guys, at this point, it is exam review free for all time. Please ask questions. Share with me how confused you are. Whatever is helpful. Yeah.
How do I do, like, I don't even know. Wait, hold on. Go back.
Okay. We'll circle back. Yes. Yeah. Go ahead. Yeah. Okay. We're going to review how to find the tangent plane because Loyan says so. Yeah. Sorry. I like repeating things. Okay. How to find the tangent plane to a function. How do we find the tangent plane to a function? There's a tasty way to do it, even if you're not a foodie, not to be confused with a baddie. And what is it? You said I use people's names, so I'm going to have to go with it. Alright, oh, look, my Apple Watch, we have a rage quit. Alright, what do we have, guys? Tangent plane.
Grad of F?
Yeah, so we have our surface, F, let's just go with x, y, and the gradient of F, tell me more.
Is a perpendicular line, always, to each point.
Yes, the gradient is the normal vector. So the normal vector to the tangent plane is the gradient of F.
Yeah.
Right? Does that make sense? At that point, P naught. So what is the equation? If you know the normal vector to a plane, you can already tell me the equation of the plane, right? Yeah, hang in there.
Sorry, I have a question.
Yeah.
Why does A have to be
Well, I guess by this metric, it doesn't have to be. So, I think I need to clean this up a little bit. What I might be trying to say here is, this is for, wait a second.
It's only because the eigenvectors have to be perpendicular, and that's the only reason why that simplifies to that.
But there's no reason they would have to be, because V transpose V, whether or not they're perpendicular or not, is still the magnitude squared. So it might not require that it be symmetric, but I have it mixed in there somewhere where something is symmetric, so stay tuned. But for Hessian, it's fine. Why? Because the way that we find the tangent plane is we take slices, if this is x, y, and z, we take slices in the x, z plane and slices in the y, z plane of our function, right? And we are tangent here, where this is flat. So the two vectors that form the plane, the two vectors that span the tangent plane, are going to contain the partial derivatives, right? Because what is the slope of this line? Oh, well, I mean, this doesn't have to be this; it could be this. I don't know why I made it a critical form. You guys my drift? This vector goes 1 in the x direction, 0 in the y direction. And what is its slope? Df by dx, right? And this vector goes in y, z. What is its slope? Yeah, df by dy. So it goes 0 in the x direction, 1 in the y direction, df by dy is that change. So when we have two vectors in the plane, we can cross them to get the normal vector, and that ends up showing us, that ends up creating a vector that is the gradient. And so guys, if we have the gradient, what's the equation of the tangent plane? What's the first piece?
A normal vector and...
Yeah, and we have the normal vector is the gradient, right?
Yes.
So the equation of the plane, if we have the normal vector, is...
Grad f dotted with...
Yeah, or but I'm going to expand it. df by dx
At p naught.
at p naught times x minus x naught plus df by dy
Y minus y naught.
y minus y naught. You got it. Okay. And that is equal to
Z.
z minus z naught.
So all we have to do is move the z naught to the other side to solve the z.
And you plug in, yeah. Because the equation of a plane is what? X, coefficient to x, ax plus by plus cz is equal to d. Okay. Yeah. Oh, yeah. Yeah. So actually, sorry, here. Yes. Yes, we're good. Okay. Oh, guys, by the way, the notes that Evan posted after class, the WTF notes, they're technically called the TLDR, but I like WTF notes. They're amazing. Look at them. Because I say so much in lecture, and they managed to get it all into one, like, really continuous talk that's short and to the point, unlike many of the things that I do. So, food for thought. More questions? What topic could show up on the exam now and you'd be like, I'm cooked? All of it.
Maybe you should tell us your computer science test. You can do the practice problem over there, see what we don't know.
I mean, but some people want to be alone with their thoughts and then so solutions to the practice midterm I'll post on Sunday. Is it late? Because I'm afraid that if I post them now, you'll be able to play that mental game where you look at the solution and be like, oh yeah, I could have figured that out. No? Saturday, okay. We will post the solutions on Saturday. Rukewa, Evan, and actually, Ruke, you are our master of Canvas. If you could post them tomorrow, the solutions, that'd be awesome. All right. More questions, guys. We have 6 minutes. It will be entertaining. It will be okay. I believe in all of you. And based on what I've seen in office hours and from your PSATs, like, you all know what you're doing.
Well, because are the questions going to be conceptual?
No, they would, like, you'll actually work stuff out.
We spent so much time doing concepts that it feels like, I feel like we know it verbatim.
I see.
Kind of.
You do.
Yeah. No, I mean, so there will be some, like, reasoning this by geometry, like, draw stuff. Like, draw stuff. Wait, okay, so has everyone played with the matrix vector applet?
Yes.
So this is the part where I get a lot of chalk in my eyes and start saying things, okay? Number 1, I got chalk in my eye. The matrix vector applet is a useful thing to be able to do in your head. Like, just imagining what it looks like. The shortcuts for figuring out eigenvalues. Ow, my eye. Really useful stuff to remember too. Let's talk about that briefly. What's the shortcut for 2D eigenvalues? You have a matrix A, B, C, D. What are the eigenvalues? M squared, or M plus minus square root of M squared minus the determinant. Yeah, what is M? The mean, which means A plus D over 2. And that's A plus D over 2. Okay. What is the equation or the shortcut for the eigenvectors? B lambda plus minus minus A. Okay, very cool. This is a useful one to remember. Now, this kind of equation you've seen it before back in your single variable calc and like pre-calc phase, right? It's in quadratic because it shows up in the quadratic equation. We had a rapper who was in the Chocolate City, which was the floor above my house where I lived in undergrad, and he became a rapper shortly after graduating. And then I listened to one of his raps, and it had the quadratic equation. So I wondered for a bit. But Edwin's got me into this rapper whose name is Yeats, Y-E-A.
Ooh!
Yeah, I don't know how I feel about it, because I don't really go for rap normally, but every now and then a song will do it. Masked Off by Future did it for me many years ago.
Wait, what's on my Yeet then?
I haven't found one
Sound
yet,
good?
but I'm trying really hard. Anyway, so quadratic equation. What do we call this part of the quadratic equation, the square root of the something? The discriminant, yes, that's the discriminant. And guys, what kinds of things could the discriminant be? It could be positive. Oh, because the discriminant was the inside part? It was like a little delta? Yeah. Okay. Anyway, just be open to discriminants. Don't discriminate in discriminants. It could be positive, they could be 0, they could also be negative.
If they're negative, that means...
And you've got what kind of eigenvalue? Imaginary eigenvalue. And guess what? That's okay.
Really?
All right. Hi.
Never mind.
You sure?
In a bit.
In a bit? We don't have a bit.
Of course.
Oh, cool. What's up, Samples?
No, I just had a thought. Like, I already know, like, there's like a formula, I think, for like a test for like finding like if something's a max or a min, like fxx and fyy.
Yeah.
And I think the determinant is of the Hessian. Using like that discriminant is that.
Yeah, determinant of the Hessian is another way to arrive at the same thing. Yeah.
Yeah.
Let's chat after because I'll show you more about that.
Yeah.
All right. More questions. Are you all good with chain rule? You all mess with chain rule? Who in their bio they said they mess with phobias. Oh, it's fun. Yeah. You said you mess with arachnophobia.
I do.
Yeah. Yeah. So does that mean that you test your thresholds of fear, or
Well,
that you
like,
have
I
arachnophobia?
appreciate it.
Oh, okay.
I appreciate it.
You appreciate the fear of the arachnids?
Yes, I appreciate it. There was that movie there in the 90s. All right, more questions. Chain rule we feel good about. Quadratic approximation is very useful.
Vectors? Like, are we going to do like vector multiplication? Volume?
No.
No.
No, I can tell you
You
that.
should fear me now.
Okay. So no vectors.
Hey guys, projections are useful.
Spiders?
Okay.
Remember the bit about your siblings and not wanting to be like your siblings?
Yeah.
Yeah. Bless you. That's what worth one to sneeze out during the test. Is talking about the projections and components and whatnot. Do I have any more hints to drop? No. During the exam, guys, we'll give you an exam paper, and then you will do all of your work and answer everything like you did our P-set on separate paper, and then at the end you'll come up and you'll scan it to Gradescope, and we will have a grading party. Are there any more logistical questions about the exam? Yes?
Where is it?
It is here.
Oh, here.
More questions? You will be okay. Go have lunch, breathe, and do chemistry. It'll be fun. All right.
I'm so hungry for this.
Yeah, thank you. It is not intense.
So like I searched it and I found it, but it's not.
Did you fix it? But I can also do it. I didn't realize the module was worked that way. If you have any unpublished modules, please tell me. All right. This has been discussed, but one of the other ways to